we're going to have this small section about Bayesian numerics. And usually when you think about Bayesian numerics, of course you're thinking about using numerical methods to solve Bayesian problems. And here I'm trying to do the other way around, which is to use Bayesian inference to attack a numerical problem, which is the problem of solving Laplace's equation. This work was done together with Edson Jr. from the University of Brazil, a colleague of mine. He couldn't come. And I divide the talk into 3 parts. So first I will tell a little bit about Bayesian inference for numerical methods, and say a little bit about Laplace's equation, and then I'll show the method for you, what I have done here. So when you think about numerics, not all numerical methods, of course, but a lot of them, it's very close to inference. So you have a problem that you cannot tackle directly, you cannot have an analytic solution, and you try to make some approximation, and try to, in the end you have to estimate the true solution using only partial data or a simplified version of your original problem, something like this. So even though it feels like inference, not always there is a direct connection, not always it's written in the language of inference using probabilities. So in some cases, yes, for instance, least squares, which was firstly devised to fit a function. So you have a function that is close, the closer you can get from a sample point. And later we know that it's related to regression, so it has a good probabilistic interpretation. And of course, many other methods as well, like interpolation, smoothing, filters, many of them can have probabilistic interpretation. And what you gain about using probabilities here, that you gain a lot of a very powerful language to ask questions about the method. Things like what are the error bars, uncertainties, information you can get, Bayesian experimental design, and so on. So I think that's what I'm trying to do with Laplace's equation, that is to formulate it as a Bayesian inference problem. And I'm doing this in the spirit of the work of O'Hagan in the 90s. His core idea, was to use Gaussian process for designing numerical methods. So it's a very general idea, and you can apply to many special cases or many situations. And it is, you have in many numerical methods, you have some function that either you don't know or you are not allowed to know. For instance, when you are computing a quadrature, even if you know the integral, you cannot use the value of the function in all points of the domain because they are infinite. So you have to either artificially or naturally, you have some partial information about the function. And what he proposed is that we treat this as a problem of inference and assign a probability to this function. And he used a Gaussian process. And then you update the probabilities using the information you have, and this can define some numerical method to compute many things. So he formulated quadratures, interpolation, smoothing, optimization, all using this language. Of course, here I'm trying to do the same with Laplace's equation. So of course, this equation, the Laplacian of a function is 0. And usually it's formulated like this. You have this equation and some boundary condition, which can be boundary of the Dirichlet type, that is, you know the value of the function in the boundary of or Neumann type, you know the normal derivative, or can be also a linear combination of these two, or you have some part of the boundary with the Dirichlet condition, or and the other with a Neumann condition, and so on. Well, I choose this equation because first is one of the most simple partial differential equations there is in the market, and it's actually very useful because it appears in many different problems in physics, and so well, it's always good to have a method to solve this equation. And it's also very well studied by mathematicians, so it's so important that the solutions of this equation are named harmonic functions, and there is a vast literature on the properties of these functions and how can we handle them. Another thing is that we have a boundary formulation of Laplace's equation. These two are equivalent. And you notice here that the solution of the function in any point inside the boundary depends only on the surface integral, which of course depends on the function, the values of the function and the normal derivative in the surface, in the boundary of your problem. And of course, since usually you just know one of these two, you have to solve this equation. Solve this equation means to find the other one. If you know the Dirichlet condition, you have to figure out what is the normal derivative and vice versa. So, well, that's the problem we are going to tackle. It's useful to have a integral boundary formulation like this, because what I'm going to do here is trying to use only the information you have about the boundaries to solve the equation and forget about what happens inside the boundaries in the domain of the equation. There are many numerical methods in the market for solving Laplace equations. It's such an important equation. Some of them are specific to Laplace's equation, and usually not very general. That is the conformal maps method of image charge. You have to somehow make a lucky guess and transform your problem into a simple one, which you can solve. There is also collocation methods, and I'm most interested in this too. You have some methods where you make local expansions like finite difference, finite elements, and finite volumes. That is, you pick up your domain and discretize it. Each method needs some different type of discretization, and you try to relate each neighborhood, the value of the function, how it relates between different neighborhoods in this discretization. And finally, the method that I want to compare, which is closer to the thing I'm getting here, is the boundary element method, in which you only discretize the boundary of your problem and do nothing about the domain inside the boundary. So here is the approach I'm going to take. We have, of course, to infer this function, this phi of x, which is unknown. Since it's unknown, we assign a probability. I'm assigning a Gaussian process with zero mean, which is just for convenience. And with this, when you have set up this process, of course, you have to account for the information you have, which is either the value of phi in the boundary, or the derivative of phi, the normal derivative in the boundary. So how do you do that? And also we must first account for the fact that this phi of x obeys Laplace's equations of Laplace 0. And how we do that? first I'll talk about the boundary, which is more straightforward. The first thing we need to do is to discretize the boundary because you have an infinite amount of points there, and you have to pick up a few ones if you want to put this in the computer and have some number in there. So the first thing we do is to discretize the boundary to pick up some points there that will represent our function. And of course, since you know either the value of the function or the normal derivative in the boundary, you transform this infinite information in just a list of points which contains information, for instance, of the value of the function in the boundary. We also you have some flexibility here since we know this thing, you know, this phi of I. Imagine that I is a point in the boundary. Since it's in the boundary, you can think about parameterizing the boundary, and this will become a function of some parameters here, this stage of t. And we can consider as valuable information here, not only the values of 8 different points, but also we can take basically any linear transformation over it, like its derivatives. You can compute quadrature. Any of this information can be used in this context, and it's good to have some flexibility because some information may be more useful than others to get the solution. So now the hard part is, well, we should account for the information in the boundary, but we must also impose that the Laplacian is 0 inside the boundary, the domain of we want to solve this equation. One thing we could do is to discretize the domain and impose, since this is a linear transformation of phi, we could impose this information over all points in your discretized domain and try to solve the problem like this. But unfortunately, if you want to solve the Gaussian process using this scheme, we will get very large matrices which are non-sparse. And when you compare it to other methods that try to do something like this to discretize the domain, you have usually you get very sparse matrices, and this will be, from a practical point of view, this approach is not very good. So what we need to do is to figure out a way to come up with a Gaussian process that already guarantees that the Laplacian of the function is 0. So if we could do that, we would only need to account for the information of the boundary. And that's what we're going to do. There are many things you can control when you pick up the covariance function of your Gaussian process. For instance, you can control how many times the sample functions will be differentiable. You can compute, you can control what are the scales for the jiggling of these functions and the variances and so on. And also, that's the thing I'm interested in here. You can constrain the sample functions to some subspace of functions here. It's the base of this subspace. And to do this, you only need to write your kernel like this summation of these functions. And here is a weighting factor that tells us how important is each function a priori in this summation. So that's what I'm going to do. I'm going to pick up a set of basis functions that already that expands the space of solutions of Laplace's equation. That you can write all harmonic functions with that. What we need actually is not very hard to find what these guys should be, but what we need here, since the set of harmonic function is a space with an infinite dimension. This summation is infinite. And of course, we need to find some closed form expression to use this in practice. So that's the problem. Unfortunately, I can't do this. Well, I can try hard, but I could not manage to find a closed form expression in 3D. So I'm working only on 2 dimensions. And in 2 dimensions, it's very easy to, not so very easy, but you can find some nice expressions because there is you can explore the isomorphism between harmonic functions and complex analytic functions. That is all harmonic functions is the real, either the real or the imaginary part of some complex analytic function. And when you do this, if you have some analytic function like this, there are some small constraints here. And you take the real part of this function, like this phi of x and y, the real and imaginary part of the argument. When you do this, if you write your kernel like this, that is instead of the real argument, you put the dot product of the 2 arguments of the kernel. And in the imaginary part, you put the vector product of these vectors. If you do this, you get a valid kernel. And these kernels, you can easily prove that they obey Laplace's equation and do the trick that was required. Well, unfortunately, it doesn't work in 3 or higher dimensions. We have to figure out other methods in this case. But anyway, here's I made some, pick a very simple example. So we have here like a small house, dog house. This is actually the inference. I don't remember here how many times I divided this boundary, but I think it was 2 or 3. Each of these lines was divided in 3. And this is actually the inference of, I picked up some random harmonic function, calculated the Dirichlet conditions, and tried and use this method to try to infer the function, the real solution from this information that was given. The difference between the real solution and the estimated one is actually very small. So I didn't put here in this graph because the lines, the control lines would be very close. And here's the graph of the difference between the 2. So we have, you see here that inside the domain, the difference is almost 0. It's very close to 0. And when you go further, you get higher values. But the convergence is really good. Here is comparison, the same problem as before, but now since Laplace's equation, you have this boundary, this integral boundary formulation, where you only need the value of the function and its normal derivative in the boundary. Since I was giving the value of the function, we need to estimate the normal derivative. And these graphs represent this here. So I parameterize the boundary. Since it's a line, I pick up from 0 to 1, we run all over this small this polygon here. And this red line here is the true value of the normal derivative. And here is the estimate I made in the solid line. Is the estimate this method gives for the normal derivative using only 5 points, 1 point to each of these surfaces here. And the dots here is, I'm comparing this estimate with the ones given by the boundary element method. And you see they're pretty close. This graph here is just the difference between the true solution and the estimated. And of course, this is very crude. because I'm only using 5 points. I could divide each of these panels here in this, I think, was divided in 3. And so when you do this, of course, you improve your solution a lot, and it is the same thing as before, but with a much better accuracy. And here's the I'm comparing the difference between the solution in each of these estimates, and you see that we very close estimate here. So this means that we are solving with very nice accuracy this problem. I'm solving Laplace equation. Well, it's only I had some problems in the beginning to get this to work, so I could not advance very much. Here I just compared with the boundary element method dimensions. And there are many similarities. I mean, the biggest one is that both methods, this Bayesian method and the boundary element method, they just need to discretize the boundaries, so which is a very good feature of those methods. And in both cases, we transform the original problem of solving Laplace's equation to a more tractable problem of solving a linear system. And this linear system is usually, you get full matrices, they are non-sparse in both cases. Some advantages of this Bayesian method is that these matrices here are symmetric, and in some cases, depends on which kind of information you account, you use. They are also positive definite matrices, which is a huge gain if you want to do numerics, because it's faster and more stable to use this method. Also, it seems I have made only very early comparisons between the both methods, but it seems that it usually has a faster rate of convergence if you discretize the boundary with more points. You get closer to the solution faster using the Bayesian version. And you also have a lot of flexibility on how you want to treat the boundary or the domain, the boundary information, which can be used to improve the method, the accuracy, or maybe the speed of this method. I have to work with this. And also in the boundary element method, sometimes you get some tricky integrals, because what you do in the boundary element method is to use the integral formulation, and you try to discretize how the function works with the boundary. And you get to solve some integrals, and sometimes they're tricky because some of these integrals are singular, and you have to handle them with care. And we have no such problem here. And finally, the bad things of this method is basically the condition numbers. You also have to calibrate the parameters of your covariance function, but it seems that the method is very insensitive to this calibration. That is, you can change the parameters a lot and will not affect the outcome very much. But the really bad thing is that usually you get really bad condition numbers, especially when you are very close to the solution. The condition number of these matrices grows very rapidly. For complex problems, this means that sometimes you cannot solve if you do not have a stable numerical solution for the system of matrices. Well, finally, I must emphasize that this method is in the very beginning and have a lot of work to do, but it seems to be promising. I only need to see if this can be, the condition numbers can be, the large condition numbers can be avoided in large-scale problems. It's good to solve simple problems like this one I showed you before. And of course, I had to work on the 3D formulation because it's more useful, and maybe also consider other partial differential equations that can also handle using, for instance, the boundary element method. Probably they can be adapted in this context too. But the good thing is, I think, in my opinion, is that this probabilistic formulation opened many doors for asking other questions that are not usually asked for classical method. So, of course, in classical method, you also do analysis of error, but here you can get probabilities and you can interpret these errors more precisely. You can also have a problem where you have uncertainties in the input data, that is, you know the boundary conditions, but with some Gaussian error. If this happens, the method works, can be modified very easily. And also there are other questions, like we can explore utility entropy using, for instance, trying to create better discretization of the boundaries using, for instance, Bayesian experimental design. There are a lot of things we can try to explore using this method. So that's it. Thank you.
I would just like to support this work. I have felt very strongly for a long time that the whole of numerical analysis is an inference problem with partial data, where you have just a few points and you're trying to infer functions. So it's natural that this should all be cast in the Bayesian point of view, and I think for the future it may well become so. Because 20 years ago I reported at this conference some preliminary work on Bayesian solution of ordinary differential equations. It was ahead of its time, but I'm delighted to see that this work is coming along now, and I wish you very well with it.
Thank you.
Can you comment on the computation time you need? Because most Laplace equations are of a pretty large dimension. So if the scaling is k to the power of 5, then you will have a problem.
The thing is here, you have to discretize the boundaries, and you get a matrix. If you discretize, for instance, 100 points, you get a matrix 100 by 100. You have to solve the system. So there is a problem because when you increase the dimension, you have to use more points to discretize your boundary. And if you do a quick calculation, it's very efficient in 2 dimensions. In 3 dimensions, it scales more or less the same as if you discretize the boundary inside the boundary. If you discretize the whole domain, and in 4 or more dimensions, it's probably better to discretize the domain than to discretize the boundary. So, but it's really fast for 2D problem. You only need a few points.
Maybe I wasn't paying very good attention and I missed it, but where's the Bayesian part?
The Bayesian part is here. You have to infer this function, which is the solution of the Laplace equation, and you assign this prior Gaussian process to the function, and use base rule basically to update this probability to account the information of the boundary.
Well, maybe it's just me. I'd like to see that made more explicit.
Okay, but we can talk later, but it's very straightforward Bayesian rule.
You had a slide which had the expansion of that k function earlier. Yeah, I'm just wondering, is that a typo, or can you just get away with UI, not UI, UJ, X prime?
Bayesian.
No, it's
UI.
Purely diagonal.
Yes.
And the coefficients are purely positive because you got QI
they are
squared?
purely positive. If they're not positive, you don't get a positive doubling kernel. And the difference here is that you evaluate the same function in x and x prime.
Any other
If
questions?
you had maybe two, if you had two integers, maybe it would be easier to find multiple solutions than this one.
Okay, any other questions? Please thank Fabio again.